So today we're going to spend a second day or a third day talking about section 3.4, which is all of this position, velocity, acceleration. I call it particle motion information. What we're going to do today is sort of look at some questions, one of which we're going to break down into really, really detailed explanation, and the next one, which we're not going to spend quite as much time on, to sort of make sure that you're really understanding what's going on. So, here are some types of questions that I can be asked with position, velocity, and acceleration in mind. A particle is moving along a line so that its position at any time t is greater than 0, that's an important piece of information, is given by the function s of t. Keep in mind this is the position function. Where s is measured in meters, that's telling me what units to use, and t is measured in seconds, again telling me what units to use. When you're reading a math problem like this, it's important to pay attention to the relevant pieces of information. So watch for important numbers or units or functions that might be helpful when you're solving the problem. For part A, find the displacement of the particle during the first 2 seconds. When I see the word displacement, I know that what this is really asking is how far away is the particle from where it started. So, to figure this out, we need to know the original position of the particle and the ending position of the particle. What I'm going to do is take those numbers and plug them into my position function. When I plug in 0, I get 0. When I plug in 2, I get 2 to the third power minus 18 times 4 plus 81 times 2, which is 98. Now, to figure out my displacement, I would say that my displacement is 98 minus 0, which is 98 meters, because I'm measuring how far I've traveled. The second kind of question I might ask is find the average velocity of the particle during the first 4 seconds. So what is this really asking? This is asking for the slope of the position function between t equals 0 and t equals 4. So, to figure out the slope, which is the average velocity, I would do s of 4 minus s of 0 over 4 minus 0. Now, if I calculate s of 4, I would have 4 to the third power minus 18 times 4 squared, which is 16, plus 81 times 4, which is 100, minus, I know my original position is 0, divided by 4 minus 0. So I get 25, and because I'm finding a velocity, that would be meters per second. The next question that I might be asked is find the instantaneous velocity at t equals 4. When I see the words instantaneous velocity, I know that the question is really asking for the derivative of position at t equals 4. So first I would take the derivative, which would be 3t squared minus 36t plus 81. Then I would plug in the number 4. So I would have 3 times 16 minus 36 times 4 plus 81, which is negative 15 meters per second. Again, velocity, so I'm using meters per second here. Next, find the acceleration. For acceleration, I know I'm really asking for the derivative of velocity at t equals 4. So my acceleration function would be 6t minus 36. And at t equals 4, I would get 24 minus 36, which is negative 12 meters per second squared. Again, seconds squared is in acceleration units. Next, at what values of t does the particle change directions? When I think about change directions, I'm thinking, make my velocity function equal to 0. This tells me when I stop. Then, look at the signs of velocity. It might be helpful here to make a chart and see where they change. So, first let's make my velocity function, which is 3t squared minus 36t plus 81 equal to 0. If I factor out a 3, I get t squared minus 12t plus 27. Let's see, so 9 and 3. So t minus 9 times t minus 3, which means t is equal to 3 or 9. Now I'm going to make a chart. I know from my original instructions that my t's are always bigger than 0. So the beginning of my chart would be 0. Then I fill in order the numbers I got here. Then the last thing is infinity, unless somewhere in the problem it said and t stops at like a certain number, 10. Now I'm going to choose a number that's in between. So if I choose a number in between 0 and 3, like 1, if I plug it in, and I would always plug it into the factored version, 1 minus 9 is negative. 1 minus 3 is negative. A negative times a negative makes a positive. So my answer would be positive, which means I'm going right. Pick a number in between 3 and 9, like 4. 4 minus 9 is negative. 4 minus 3 is positive. A negative times a positive is a negative, so I'm going left. And if I pick a number that's bigger than 9, like 10, for example, if I plug in a 10, 10 minus 9 is positive, 10 minus 3 is positive, a positive times a positive is positive, so I'm going right. This means I actually change directions. I switch between moving right and moving left at t equals 3 and t equals 9. Now some of you might be thinking, why do I even really need to make the chart? Couldn't I just say, well, those were the zeros, so that must be where I change? There are going to be times when they don't actually change signs at those numbers. So you always have to make the chart to check to see if it actually changes signs at those specific values. Now that's really breaking down the problem. I mean, we are really talking through it, but on a quiz or a test, I'm not going to have you break it down that much. I'm going to give you a problem much more like this one. A particle moves along a horizontal line, its position function is given, so it's important to note that we're being given the position function. S is measured in meters, t is measured in seconds. First, find the displacement. If I say find the displacement, all you have to do is final position minus initial position. So my final position here would be 12 squared minus 23 times 12 plus 126, which would be negative 6. Minus, my initial position would be 10 squared minus 23 times 10 plus 126, which is negative 4. So minus negative 4, which means my displacement would be negative 2 meters. Average velocity. You'll notice that I gave you the same interval. Perhaps knowing these numbers will help us find this. Average velocity is just slope. So I would do s of 12 minus s of 10 all over 12 minus 10. You'll notice I already know those numbers. So I should get negative 1 meters per second. Now I did that on purpose, and I'm going to do that on purpose on quizzes and tests a lot of the time too to save you the extra calculations. You're using the same values, so you don't have to recalculate it again. Instantaneous velocity at 4. When I see average velocity, I think slope. When I see instantaneous velocity, I think derivative. So my derivative would be 2t minus 23. I want to know my velocity at 4, so I would have 2 times 4 minus 23. And 8 minus 23 would be negative 15 meters per second. Speed at t equals 4. You'll notice I gave you the same time as I did in part C. Speed is the absolute value of velocity. Now that I already know velocity, I would just do the absolute value of that number, and I don't have to recalculate anything. Again, I did that on purpose. I'm trying to save you from having to do a whole bunch of calculations. For part E, when does the acceleration equal 0? So first I need my acceleration function, which is 2. It's just the derivative of this velocity function right here. Does it ever equal 0? No, so you would say never. When does the particle change directions? So again, acceleration meant take the derivative. Change directions means make your velocity function equal to 0. We've already got our velocity function. So we would have t equals 23 divided by 2, which is 11.5. To figure out whether or not we actually change directions, we're going to make a chart. It does not say in this problem that you're starting with t is greater than or equal to 0. So our chart this time would start at negative infinity. 11.5 would go in the middle and infinity would go on the end. And again, we're looking at the sign of our velocity function. So pick a number less than 11.5, so 0. If I plug that in here, I get a negative number, so I'm going left. If I pick a number bigger, like 12, for example, and I plug that in here, I get 24 minus 23, which is positive, so I'm going right. So I change direction at 11.5, so I would say t equals 11.5 is my answer, and I would put seconds on there because I'm measuring in seconds. Next, when is the particle speeding up or slowing down? To figure out speeding up or slowing down, I need to compare acceleration and velocity. Now, it did not ask me whether I'm speeding up or slowing down at a specific number here. It just means in general. So to figure this out, we're going to make another chart. In this chart, we're going to have a row for velocity and a row for acceleration. Now, they're both going to start at negative infinity. Here's the numbers you put in the chart. Anytime acceleration equals 0 or velocity equals 0. You'll notice that I already solved both of those problems earlier in this question in parts E and F. The only time acceleration equals 0 is never. The only time velocity equals 0 is 11.5. Now I'm going to look at the signs for both acceleration and velocity. If they have the same sign, I'm speeding up. Opposite signs, I'm slowing down. I already made this chart for velocity. We said we were negative and then positive. Acceleration is always positive too, so it's going to be positive all the time. What that means is that because these are opposite signs, this is where I'm slowing down. And because these are the same sign, this is where I'm speeding up. So we would say we are slowing down from negative infinity to 11.5 open. And we are speeding up from 11.5 to infinity open. The reason I'm making these open is that anytime you're using the second derivative, which is acceleration, you always use open brackets. Anytime it's just velocity, you use closed. Speaking of, when is the particle moving to the right or to the left? We said for this originally we make our velocity equal to 0, we make a chart, but we already did that in part F. So we can just use this same chart to help us with this one. We're moving left from negative infinity to 11.5, and this time I'm going to use a closed bracket because it's just velocity. And we're moving right from 11.5 to infinity. And again, this time I'm using a closed bracket because it's just velocity. Okay, I hope this gives you an idea of the types of questions that I might ask and the kinds of work you're expected to do. We're going to do a bunch more practice tomorrow, and I'll see you then.